Ladies and gentlemen, my name is Ezio Cadoni. I'm professor at the University of Applied Science of Southern Switzerland. I'm going to present to you some results on the high strain rate behavior of ultra-high performance fiber-reinforced concrete in direct shear for particular application, the protection against improvised explosive device and blast charges. Over the last 45 years, we have observed a number of incidents in terms of accidental or intentional explosions that have caused significant damage to the infrastructures. In particular, the number of terroristic attacks has terribly increased in the recent 2 decades. This has highlighted the need to study the effect of blast loading on structures and also drawn the attention of the international engineering community on this field. As you know, blast loading is quite different as compared to the other conventional loading. Generally, high-intensity load having extremely short duration, causing a high strain rate in the materials. Protective structures and critical infrastructure need to withstand exceptional loads such as blast and impact. Many of these structures are made in cementitious materials, and among the very promising materials for the production of shields and protection are the ultra-high performance concrete, usually defined by their commercial name. Ultra-high performance fiber-reinforced concrete, in comparison to normal strength concrete, do not framework where these tests were developed. This work is a part of a long-term research on the protection of infrastructure from the effect of EADs and blast charges. This research is funded by the Federal Department of Defense, Civil Protection and Sport of the Swiss Confederation. The research is subdivided in 3 tasks: material characterization, numerical simulation, and it has been developed by using 2 special research infrastructures. The first one is the Hondrich Detonics laboratory. It is a modern underground test facility designed for a few instrument Detonic experiments. This laboratory was created by reusing a former artillery fortress from the Second World War. In this lab were tested different slabs with C4 contact and standoff charges. The second one is the DynaMat laboratory. This is an advanced laboratory for mechanical characterization of materials in dynamics, able to measure accurately the stress-strain curve of material in tension, compression, and shear in a large range of strain rates. This laboratory was founded by me in 2006. Since 2015, it is included in the roadmap of the research infrastructure of national relevance of the Swiss Confederation and will remain on it till 2028. This laboratory is equipped with several modified open zone bars for testing metals, polymer, concrete, rocks at a high strain rate. We have also 2 hydropneumatic machines for medium strain rate and 2 universal machines for quasi-static. With this philosophy, starting from the material testing, we calibrate existing constitutive law or create new ones. The third step is the design calibration in the final element code, and finally the structural assessment is performed with the partner. The aim of the research was study the retrofit system using ultra-high performance concrete. When a critical structure has been designed without any blast protection, it is necessary to improve its resistance capacity by means of retrofitting. Usually, we have characterized the material in a different failure mode like tension, compression, indirect tensile, and shear behavior. And in particular, now we are concentrated in shear behavior. Four materials are analyzed here, and they were a commercial product characterized by very high strength. High carbon striped fibers, 13 mm long and 0.2 mm diameter, were used. The addition of increasing percentage of in volume of steel fiber allows achieving outstanding mechanical properties such as very high compressive strength and flexural strength. The first one are coming from 178 up to 200 megapascal, and the flexural strength from 24 up to 42 megapascal. Direct shear specimen has been designed following a numerical optimization study. Short gauge length permitted to achieve homogeneous stress distribution in the gauge, also in the case of testing at a high strain rate. The high strain rate in direct shear have been carried out by means of modified open bar in compression. The system consists of two circular aluminum bars having a diameter of 30 mm and a length of 3 meters for both input and output bar. The specimen is sandwiched between the input and output bars through the special connector designed to maintain acoustical impedance constant in order to avoid spurious reflection in the interface. Input and out bars are instrumented with semiconductor strain gauges, which measure the incident, reflected and transmitted pulse acting on the specimen. The pretensioned bar is a high-strength steel, 6 meters in length, connected to the input bar and permit to store elastic energy that is abruptly released thanks to the failure of beetle bolt, causing the compression wave propagation in the system. So incident, reflected and transmitted pulse are obtained. As you can see in the slide, it's possible to obtain a very clean resolution of incident, reflected and transmitted pulses, a sharp rise time of incident pulse around 200 microseconds, and lastly, the constancy amplitude of incident pulse. On the basis of this material and considering the equation regarding the one-dimensional wave propagation, it is possible to evaluate the shear stress, shear slip, and strain rate history. In this slide, we can observe the shear stress versus shear slip curves of the four ultra-high performance fiber-reinforced concrete. Increasing the percentage of fibers and enhanced shear capacity is obtained. The deformation capacity is an incremented, allowing higher distortion to the material. This effect could permit to the structure made with these materials a higher deformation, as a result, higher ductility. The fiber orientation and distribution have a strong influence on the tensile and also in the direct shear behavior. Increasing the fiber content also increased peak stress and post-peak stress is obtained. When the orientation of the fiber is well distributed along the loading direction, the behavior tends to pseudo-elastoplastic or strain hardening behavior. The influence of the fiber percentage can be highlighted observing the comparison between the average shear strength between the different ultra-high performance fiber reinforced concrete with fiber having different aspect ratio. It is confirmed that the shear strength increased with the increasing of the percentage of fibers. It can be noted that the fiber with the same length, 13 mm for example, but a different diameter, these results, together with those in tension, compression at different sites and boundary conditions, have been used to develop a new damage model. This model, starting from the material characterization, is able to describe the structural behavior, for example, in sandwich structure subject to contact C4 charges, as shown in this slide. In conclusion, I'd like to highlight the complexity of this for your attention.